Okay, so now let's talk about pre-training. So essentially, we're moving into transfer learning. In other words, this is one scenario of transfer learning is that you can pre-train a model and then fine-tune it for a task. You can pre-train a model to get the context and then fine-tune the model for the task. Okay, so this is one of the transfer learning scenario, and I want to use transformers to explain these pre-training and fine-tuning scenarios, because one advantage of these transformers are they can, especially in natural language processing, is that they can be pre-trained by massively available data. Even though you may complain that there's very limited data for your task. So why pre-training? So we are often interested in predicting a label, right? For instance, you started with a text, you want to predict the sentiment, right? Or you want to start with an image, you want to generate a caption. So in those cases, the outputs are called labels, right? And we are used to supervise the learning with labels available, but they are very often rare, right? Think about the number of texts that have corresponding images or vice versa, or the number of protein sequences whose structures are available or functions are available, right? But in the meantime, you have to realize that there are massive unlabeled data, okay? And this unlabeled data, for instance, this text without sentiment labeled, without images available, or protein sequences without structures or functions. There are so many of them, right? We know that many orders of magnitude more, right? So we could utilize them. And I said just one way, this is one way to utilize pre-training, but it's very superficial. But let's start with that is, we can start by utilizing these pre-training to initialize part of your model parameters, and then fine-tune it for your task and and improve the model performance. Okay, but the tricky question is how do you make that happen? Right? It sounds good, but how do you make it happen? Specifically, we should look at optimization problem and ask ourselves. Right? In the pre-training, in the fine-tuning stage, it's easy. You have the supervise the machine learning with labels available. We talked about what losses should be there, right? But the question is, how do you design the pre-training tasks, including the losses, right? So that you can learn something contextual, right? Generally contextual and useful for your downstream task. That is not something that is very easy, right? So that's what we're going to try to focus on. So, pre-trained NLPs, we can start with word embeddings, for instance, right? Before 2017, we basically just use the pre-trained word embeddings themselves, right? So these are just the word embeddings without necessarily the context available, right? And then we incorporate these embeddings into LSTM or transformers, and in the same time, we add the context information there, and then train on the task, right? So that was the previous strategy, right? If you think about what the architecture is like, is we have these word embeddings that are pre-trained, right? They're in red, meaning that they're pre-trained, and these can be fed into the intermediate layers. Here I use the bidirectional recurrent neural networks, but it can be anything. And in the end, I predict the y hat, which could be the task like a sentiment prediction or completion of the sentence and so on, right? So these parameters are gray, right? So they are not trained, they are not pre-trained. So when you are training your supervised task, right? These layers are pre-trained, or these inputs are pre-trained, but most of the model parameters are randomly initialized, right? And if you think about it, that's a bulk of your model parameters, right? So, so this is the issue that I was talking about. First of all, when you pre-train these embeddings, right? So you don't know that this pre-training data we have to be whether it's sufficient to teach us about the contextual aspects of the language. And the second thing is that most parameters are randomly initialized here. So these are a couple of issues with that kind of approach, right? So what is happening now in the modern NLP is that we sort of use all or nearly all parameters that are initialized via pre-training. So roughly it's like everything, almost everything, except maybe the last 1 or 2 layers are read, meaning that they're pre-trained already. And the trick, of course, comes from how you pre-train, including the design of the loss, right? So the pre-training methods usually hide part of the inputs from the model and then train the model to reconstruct those hidden parts, right? So this is a general idea about how you can pre-train almost the entire model and why that might be a good idea, right? And then I want to say that there are 3 ways you can utilize or interact with the pre-training, okay? I said one way originally. What was that one way? The second one I said at the beginning, right? You can interact with pre-training by utilizing the model parameters and use those values in the pre-training stage as initialization value of the fine-tuning stage, right? So in other words, it's parameter initialization, okay? But you can interact with pre-training in more ways than that, right? You can, interact with pre-training by utilizing the representation of language. And also remember that these language models are modeling the distribution. So we could probably use this distribution and use a sample from these distributions and so on in some cases, right? As we will see later on. So these are the 3 ways you can interact with NLP, these pre-training NLP models, okay? So let's look at one example again. Recall the language modeling is, this is what we did for the decoder. Remember, I was asking why did we do masked, self-attention, right? Because when you try to reconstruct a WT, you can only look at the past, 1 to t minus 1. You cannot attend to the future, right? So this is, what we talked about earlier. So when I say language modeling, by default, I'm looking at this distribution, right? So this decoder is very useful for what kind of task, especially when you are generating a sequence, right? This is autoregressive because you can generate the first and then feed that back to the input of this first position and then generate the second, then take the first 2 and feed it into the first 2 inputs and then generate the third. So you can use this decoder to sample, right? The third way to interact with pre-training, right? And you have lots of data, right, for this kind of modeling, right? So you can train a neural network to perform this language modeling, which essentially give you the loss function already, and then save the network parameters and then use them to initialize, right? So this is again just a little bit more detail, right? So in the pre-training stage, you have a lot of data that are unlabeled, right? And you sort of try to learn the general things like a context, right? And in this case, we look at language modeling, right? P of xt given x of t to t minus 1. And then in the fine-tuning stage, we are utilizing the task-specific labeled data, right? This is very few data, by the way, right? And we're trying to adapt these, mostly, almost, initialized, completely initialize the decoder, and then adapt them to the task, right? So this is based on a different test of data, and then the loss is also different, right? The pre-training loss and the fine-tuning loss are different as well, right? So this is what we do, right? So why do we believe this kind of pre-training fine-tuning stage approach might work? I'm going to ask you to think about these questions from the perspective of optimization. In the pre-training stage, you have a loss L pre-train a function of all the model parameters theta, right? And you minimize that pre-training loss and get a optimal theta hat in the pre-training stage. Then you're going to use that theta hat to initialize the theta when minimizing the L fine-tune of theta in the fine-tuning stage, right? So why do we think this approach might be helpful? Any ideas? From the perspective of optimization. What assumptions are we making? What is the rationale of this pre-training fine-tuning in the perspective of optimization? Well, you have to think about it that we are using stochastic gradient descent mostly. And we are assuming that when you're optimizing such a high-dimensional, non-convex optimization problem, right? And you start with theta hat, your SGD is actually not gonna, it's minimizing a new fine-tuning function or loss function, right? But your SGD is not gonna deviate too much from theta hat, the starting point. Okay, that's one major assumption, right? So it's gonna be explored a lot bit, like really fine-tuning, even in the sense of optimization. It's like sampling around the theta hat by the SGD a little bit for the new task under the new fine-tuning losses, but it's not gonna be, in a completely different region from theta hat. In other words, it's not gonna be completely forget about the knowledge distilled into the decoder through the parameter initialization. So that is assumption. Okay, so again, optimization is very important to machine learning. Okay, let's think from that perspective. So how do you pre-train? Also, sort of depend on this architecture kind of affects how you pre-train. Okay, and also it affects the utilization of your pre-training. Right. Again, I give 3 kind of examples here. Right. You can pre-train the decoder. That's something I talked about already. You can use the language models, which by language models you know what I mean. It's probability of xt given 1 x sub 1 to t minus 1, right? So that's the probability I'm trying to reconstruct, and that's the loss I'm going to use in the pre-training stage, right? And it's very nice to, you cannot condition on future words, but it's very easy to generate or sample a sequence from the decoder, right? As I said, you use a start codon as the input, a token as the input, and you get the first y1, right? You use a start, and then you get a y1. Then you feed this y1, right, back to this second position, and then you get a y2, and so on, right? So this is sort of autoregressive way, right? And the examples include GPT and GPT-3, the latest ones, right? If you want to talk with a robot, GPT-3 might be one of the smartest ones, although sometimes they think in a different way than we do, right? Then there's an encoder, right? I want you to pay attention to the difference between the decoder and encoder also through this connection. Did you see that? The connectivity between these, input and the hidden layers, right? Or the input and the, and the hidden layers are actually different. Did you see that? Right? Again, in the case of the decoder, right? If you look at this one, right? It only depends on the current input, right? This is H0 only depends on X0, right? H1 depends on X0 and X1. H2 depends on X0, X1, and X2, but not X4 and X5. These are the future. Okay, so pay attention to that. But for decoders, it doesn't matter. You have the bidirectional context. You can condition on the future. That's why you see these arrows, right? Actually goes much sparser than this, much denser than the decoder, because you allow the bidirectional context. Okay, so one example is BERT, right? If you heard about the BERT, and their variants, right? The B actually stands for bidirectional, right? So how do we pre-train them? I haven't taught you what to do, but we'll talk about them very, very soon. And then we'll talk about, sometimes we have both encoder and decoder as the example of image captioning, right? And the other examples we talked about. And we can get the good parts of both, right? But, transformer T5, they are encoder-decoder architecture, right? So what is the best way to pre-train them together, right? So that's something we're trying to talk about in next. First, decoder. This is very easy, as I said before. We are pre-training to predict this probability distribution, right? So, these are the layers that we can initialize, right? And in the end, for the task, we can introduce in the fine-tuning stage, the task might be predicting the sentiment, right? So I take the last hidden vector and then go through a very simple linear layer and then classify them, right, into different sentiments. And all but A and B, this linear layer, would be initialized, right? So these A and B are very small amount of parameters compared to the whole to the whole model, okay? And then of course, the gradient will propagate through the whole network in the fine-tuning stage, right? So this is the pre-training the decoders. And what I said was one way so far about to interact with pre-training. Basically, I'm saying that you can initialize these parameters a lot, right? But remember, we can do more ways to interact with the pre-training, right? So you can use the pre-training as the distribution, right? So we can utilize the distribution, right? And in this case, we can use this distribution as generators and fine-tuning this distribution, right? For instance, again, depending on what your final task is, right? But it could be that I'm trying to have different kind of tasks constructed, right? I have this input words and then this output words, and then I go through the hidden and the readout layers, which is linear in this case. And I could introduce different kind of tasks. One is sort of the dialogue, right? So the context is, we can have a lot of dialogue data, right? So we can learn the context from the dialogue history. We can also, right, try to get an output, for instance, from the last layer, and which is a summary of the whole document, right? So remember, there are some, lean browser which give you a summary of an article or a web page, right? So that's the kind of task about the summarization. So you could have different kind of outputs, and depending on what kind of pre-training task you are introducing, and then you're basically, using those to introduce the context, right? As long as you have a lot of pre-training data for that purpose, okay? So notice that now even the linear layer can be pre-trained, right? So in other words, you can think of this way, right? Instead of change the model architecture a lot from pre-training to the fine-tuning, right? Or between the unsupervised and the supervised task, maybe I can change or define my pre-training tasks in a way that I can borrow the same architecture as much as possible, right? This is a different philosophy. Do you see that? Right? Because you want to train your model parameters as much as possible, right? And previously we keep thinking that, well, we're going to utilize part of them, and then there's going to be some part that is not initialized. But you better make that part as few as possible. So it's entirely possible to change your pre-training tasks and utilize almost the same architecture so that almost all the parameters can be initialized and pre-trained. Okay, so that's the idea. And GPT is one example, right? So that was the big success, and I don't want to talk about the specifics. And this is this is the, how do you pre-training the GPT, right? So this is how you pre-training the GPT. So the way we pre-training the GPT is very interesting, right? So it's basically giving you, it's like a dialogue, right? So you have two texts actually. Let me see whether I have that web page. I don't. So imagine that you have two texts, right? And the relationship between the two texts, right, can be one of these scenarios: entailment, similarity, or multiple choice. Okay? So for instance, there are two sentences. One sentence says that, I sit in Zachary. Okay? So that's one sentence. A student is sitting in Zachary. That's one sentence. Another sentence is saying that, someone is a PhD student who is taking a class in room 316 of Zachary. So it's like the second sentence is, giving more information about the first. It's called entailment, right? And you could have similarity, like two different sentences saying essentially the same thing. So you could have different relationship between these two texts, right? But how do you change this, sort of, dialogue? We're trying to find out this dialogue context, right? So that goes back to my question, right? So I want to make sure that my architecture almost does not change between the pre-training and the fine-tuning, right? So for my fine-tuning task, I might be just give this, sentence and then, try to predict the sentiment or, predict the, or generate the image even, right? So how can I construct the pre-training task utilizing this, context of dialogues, so that my architecture can be almost the same? So this is how they do it, okay? So they basically concatenated these two texts together. Do-Young, do you mind talking about your slides next time? Oh, yeah. I wanted to finish the pre-training and language models. And yeah, on Thursday, yeah. And also next time I will start talking about the generated models, then that also echoes your GAN, okay? Sorry about that. So I think this is really interesting. Let's look at it. So you have two sentences, text one and text two. But I sort of combine them into one sentence. So I introduce a start token, and then the text one is tokenized at the word level or character level. Then I introduce a delimiter between these two sentences. Then I have a text two. And in the end, I have an extract, right? So you see that this is very similar to what I would provide to my architecture for the fine-tuning task, isn't it? Right? So in other words, you are formatting these pre-training inputs as if they are going to be used for the fine-tuning, right? Because you want to use your fine-tuning, you want to use your pre-training architecture almost covering the fine-tuning architecture. So what we are going to do here is, we are going to look at the embedding of the extract. That is the last token. And then this embedding of the extract, right? Of course, this will be fed into the self-attention. In the end, we read the embedding of the last token extract. And then we'll go through the readout to do these linear classifications, right? It could be one of the three relationships: entailment, similarity, or multi-choices, and so on, right? So that is one way, right? So in other words, the linear classifier itself was already pre-trained by classifying this relationship between the two sentences. Okay, isn't that fun, right? So and that was using the embedding, right, transformer learning embedding of the last extract. Okay.